So momentum is conserved. Why? No external, oh, that was unfortunate. No external forces. Okay? If my system is the rod-like human and the Nerf bullet, then the forces between the bullet and the rod are internal to the system. So its momentum is conserved. From this, what do we deduce? The rod must be translating. So what is that? What does that mean?
It's translating and spinning.
It's both translating and spinning. So are the points on the rod moving at the same velocity? So when you say the rod is translating, the center of mass is translating in order to conserve momentum. So let's see. So what's the initial momentum? So if we call that direction x, I guess it would be mv naught in the x. And that must be equal to, all right, what's the momentum of the whole darn thing afterwards? We're going to treat it as though all the mass were concentrated at the center of mass. How much mass do we have? Okay, m plus little m, right? We have the total mass, which is the mass of the rod plus the mass of the embedded bullet, times the velocity of the center of mass. I have skillfully avoided figuring out at the moment where the center of mass is, but this must be true. Okay? So this is a statement of conservation of momentum. What don't we know in there? Yeah, so now we know VCM. So we know that the velocity of the center of mass must be equal to okay, so that's what we learn out of momentum conservation. So the center of mass of the rod plus bullet slides to the right at that speed. What's next? Yeah, well, the other thing that's conserved is angular momentum. Now we want to exercise our freedom of choice to pick a convenient reference point. Well then, I mean Gesundheit. All right, so what would you pick as a convenient reference point to simplify the calculation?
You can use the center of mass as the reference.
Okay, so one argument is use the center of mass. Where is the center of mass? Somewhere, yeah, okay, good idea. All right, so if we have the distance d, let's call that y. How do I find y for the center of mass? Yeah, it's a uniform rod, right? So do I have to do any integrals? Please say no. Sherry, do I have to do any integrals? You sure? Okay, how do I do it then? How do I calculate the center of mass position? YCM. Okay, first moment with respect to y. So I can treat the whole rod without the bullet as though it were concentrated at its center of mass, which is at d/2. So this is mass of the rod d/2 plus mass of the bullet d over m plus m. So the center of mass will be at d times 1/2 m plus m over m plus m. Yuck, or lovely, or whichever. Is there a simple way to check, like a simple value we could use to check whether this is screwed up?
Sure, you use 1 0.
Why don't we use the same mass for the bullet as the rod? Then you should be able to tell me immediately where the center of mass should be. 3/4, right? Halfway between the center and the bottom. Does it work? 1/2 plus 1 is 3/2 over 2 is 3/4. It works. Okay, and that's right. And there was much rejoicing. Okay. So we now know where the center of mass is. Why did we care? Ian suggested that he wishes more rotten tomatoes. He suggested that we use the center of mass as our position for computing angular momentum. Right? Is that a good idea or a bad idea?
Not that bad of an idea. It's a bad idea.
Anybody have a better point? End of the rod. Okay, what's your reasoning? I like it. Therefore, yeah, and therefore, well, okay, so she's making an argument that that's where all the forces happen, and so torque is 0 initially. Now she's moving off into the realm of the wrong. So we want to avoid that realm. Is the bullet not part of the system? It is, right? So the forces between the bullet and the rod are internal, so we don't worry about torque from them because of the action-reaction pair. They're going to cancel out. But I like, what's the advantage of picking the point at the end of the rod where it is initially, where the collision takes place? Yeah. Yeah, the initial angular momentum is 0. So what's the final angular momentum? 0. Okay, so we could use that way. Let's do it both ways. We'll do Ian first. No. What did you do? You suggested, okay, fine, I'll put it up here. Okay, so what's the initial angular momentum about the center of mass?
You're going to get disemboweled anyway.
What's the initial angular momentum about the center of mass? Well, center of mass is sitting there. The bullet's coming in here. So what's this distance? D minus YCM times, right? So R cross P So if we go about the center of mass, there's no orbital angular momentum. There's only the spin angular momentum about the center of mass. R cross P, momentum is perpendicular to that distance, and so we would get d minus ycm times mv naught. And in the out of the board direction, oh, I prime looks like a pain. So angular velocity would be d minus ycm mv naught over I prime. Well, just for grins, let's calculate I prime. No, too bad. All right, I prime. We have to heal the emotional scars over the parallel axis theorem, people, all right? So, it might be convenient to know how far the center of mass is away from the middle of the rod. So let's figure out how far the center of mass is let's call that, give me a letter. Q. Q, I love it. Okay, Q. All right, let's find Q. Q is equal to YCM minus D over 2. I don't want to do any integrals. And I want to use the parallel axis theorem on who? Yeah, I actually would, but in the moment I'm going to use the parallel axis theorem on the rod. The parallel axis theorem, let me remind you, says that the moment of inertia rotating about an axis parallel to an axis passing through the center of mass plus the mass of the something. Now, these symbols here unfortunately collide with the ones that are used in the problem. So I'm going to give them under mustaches so that you're not confused more than strictly necessary. All right, Q. YCM minus D over 2. What a pain. All right, so we have D times 1/2 m plus m, m plus m minus 1/2. So that's D all over m plus m, 1/2 m plus m minus 1/2 m minus 1/2 m. Oh, well, that's nice. So these go out, and little m minus 1/2 m is 1/2 m, so we get D over 2 times little m over big M plus little m. Right? Keep me honest. Yeah?
Wouldn't it have just been easier to use the parallel axis theorem and then the moment of inertia of a rod rotating about its end, since we wouldn't have to calculate Q, we would just use YCM?
So this theorem, what does this thing mean? Of what? No. Slap him. No. We have a rod. We know that its moment of inertia when it rotates about its center of mass is what? 1/12. Okay? If I want to rotate that rod about an axis that's displaced from its center of mass, I need to know how far it was displaced from its center of mass. not from some other random position on the rod, like its end. This means the center of mass of the thing to which I'm applying the parallel axis theorem. Am I applying the parallel axis theorem to the system of rod plus bullet? Do I know what the moment of inertia of the system of rod plus bullet is about its center of mass?
Can't you
No, that's what I'm trying to calculate. Derp. What?
Well, don't you know I about 1 point, then you can find I prime about for the entire system?
Don't I know this about 1 point?
About like the end point, and then you can solve for I prime
How would I do that?
with the parallel axis theorem.
You want to do it? I think you have the problem that you need. This always has to refer to the center of mass of the object to which you are applying the parallel axis theorem. So it's going to be straightforward for me to apply for the bullet because it's a point mass. The thing that's more complicated is the rod. I know, based on the derivation, that if I use this from the center of mass of the rod and then I move the axis a distance d, that this will tell me the moment of inertia of the rod. Other things are mere speculation which turn out to be wrong, and I encourage you to work them out. Okay, so I have now the distance q by which I'm moving, and therefore I rod about the new center of mass. So maybe I better call that something. What do you want to call this? Star. Good idea. I rod star. Okay, so this is not with a bullet. This is just the moment of inertia of the rod about the new center of mass of the combined system. Well, the point I'm calling star. So that is how much? 1/12 m d squared plus how much? Big M times q squared. Okay, so I star will be equal to I rod star plus what? That's Q, right? So what term is missing here? Yeah, the bullet. So that should be M times d minus ycm squared. And then I'm missing, let's see, this was out. Okay, the rest is algebra, which I'm going to leave in the interest of time, but this expression would give me the moment of inertia of the rod when it rotates about the new center of mass. I add to that the moment of inertia of the bullet about the new center of mass. That gives me the total moment of inertia about star, the new center of mass. Okay? And that is what I need in that expression. Okay? Now, what was the other approach? The other approach was to say that that we should use this point. and then the angular momentum was 0. So the total angular momentum about that point should be 0. The center of mass will be translating to the right. With respect to that point, and it will be rotating this way. So we would have 0 is equal to the distance to the center of mass from the end, which was d minus ycm, times all the mass times VCM, and that would be into the board, right? That would be into the board, plus I about the center of mass, omega. And that better work out to be the same thing. But I'm not going to drag us through the algebra for that.